So first off, I want to thank the conference organizers for the opportunity to give this talk. This is pre-recorded because of time zone issues, but if you have any questions, please send them to me on Slack afterwards. So hi, my name is Kelly and I'm a PhD student at McGill. Today I'm going to be providing an update on the Prism experiment. I will start with some background about what Prism is, and then I will discuss where we are at in terms of data collection and analysis, and I will be specifically focused on the calibration methods since that is where I've been putting my personal efforts. Okay, so I first want to mention that Prism is a collaboration with members from various universities, both in North America and in South Africa, so you can see those relevant institutions listed here. So let's talk about what PRIZM is. So PRIZM is an acronym. It stands for Probing Radio Intensity at High Z from Marion. It is a global 21 centimeter experiment set up on Marion Island, which I will discuss where that is in just a minute. The PRIZM setup consists of two dual-polarization radiometers, and these antennas are operating at central frequencies of 70 megahertz and 100 megahertz. So together between the two antennas, there is frequency coverage from about 30 to 200 megahertz, and PRIZM has been up and running since 2017. Okay, so there are a number of experiments that explore the global 21 centimeter signal, but what makes PRIZM unique is its remote location. So the PRIZM antennas are located on Marion Island, which is a small island about halfway between South Africa and Antarctica. So this makes it about 2,000 kilometers from the nearest permanent habitation. So if we look at this map here, we can see the tip of South Africa at the top, and we can see just the top of Antarctica at the bottom, and the red spot is where Marion Island is located. So if we zoom in on Marion Island, we can talk more about the PRIZM setup. So in particular, PRIZM is set up in sort of this northeast side of Marion Island. The reason is that is where the main research base on Marion Island is located. So the island is used by a small group of South African researchers, but for the most part, it has very little activity and it's very remote. So this makes it pretty much RFI free in the frequency range that we're interested in. And this is a huge advantage since RFI, or radio frequency interference, is a major challenge for most global 21 centimeter experiments. So on top of being in a remote location, the actual PRIZM setup is also 4 kilometers away from the main base on Marion Island. So as you can see here in the photo, the main base is kind of in the upper right side, and the PRIZM experiment is about 4 kilometers inland from the base, and it is nestled behind Junior's Cop, which is sort of the highest hill in that area. So this location provides a shield for the experiment and further limits any RFI that might be coming from the main base. The downside to this location is that it is a bit of a hike to get there from the base. And also, just in general, the downside to being on Marion Island is that, as you can imagine, there are some logistical challenges. So there's, for example, a short access window each year. There's only about a 3-week period when we can access the island. There's also harsh weather, such as high winds, low temperatures. And we also have to deal with wildlife. In particular, on the island, there's a bit of a mice issue. So a bit more about the instrument itself. You can see in this picture kind of the setup here on Marion Island. So in the background you have Junior's Cop, so the main base would be in that direction. In the foreground you can see the setup of the 70 megahertz antenna, and the 100 megahertz antenna is kind of on the right side in the background. You can also see a set of shipping containers in this photo. Those are used to house spare parts and electronics and the different things we need to run the instrument. So if you look at the 70 megahertz antenna in the foreground, you can see that it sits on top of a ground screen. That screen is roughly 10 meters on a side, and the antenna pedals at the top are supported by a fiberglass structure which also houses the first stage electronics. So let's talk more about the instrument itself. So the Prism radiometers use the 4-square antenna design that was previously used by the SciHy experiment. Here you can see a schematic of the electronics. If we look at the first stage electronics, so that's the top of the picture, there are 5 switch states. So there's the antenna as it looks at the sky, and then there are 4 calibrator states. So those are 50 ohm and 100 ohm loads, and also a known noise source as well as a short state. The second stage electronics, which is at the bottom, are placed in a Faraday cage and put 50 meters away from the antenna itself so that we avoid any self-generated RFI. So for a bit more information on the data collection, the auto and cross spectra for both polarization channels are written to disk about every 4 seconds. The spectra span 0 to 250 megahertz, with that being in 4,096 frequency channels. The data acquisition rate is about 900 megabytes per day for both instruments combined. So this allows us to store several months of data on just the normal SD drive of the Raspberry Pi computer that we use to kind of control the antennas. Okay, so let's look at some data. So the top graph shows us the cadence of those switch states that I was speaking about before. So the antenna spends about 10 to 15 minutes looking at the sky, followed by 1 minute for each of the 4 calibrators. And here's some example of some uncalibrated data. So if we look at the plot on the left, the bottom, we can see the 0 to 250 megahertz range of the frequencies. And we can also see that this particular piece of data spans about 26 hours of time. So the horizontal lines throughout this plot are of the calibrator states. So of course we need to filter those out to see just the sky. So that's what's happening on the right-hand side. The top plot is after we've filtered out the calibrators. And then on the right-hand side on the bottom plot is some cross sections of that waterfall plot so that we can see the spectra of the sky here in black, as well as some of the calibrators, which are the colored lines, the yellow and blue lines. Okay, so a little more information about our data. So far, we've been focused on the 100 megahertz antenna and on data collected in mostly 2018 and a little bit in early 2019. Basically, the reason for this is mostly due to the pandemic. We haven't had a chance to get back to the island and actually physically collect the data taken in 2020 or 2021. So that's why we're still mostly focused on data from 2018. Though it's looking like in a few months, we're going to be able to get back to the island and get all of our data from the years that have followed that, so that's very exciting. Anyways, from just the 100 megahertz antenna, and again, just in 2018, we're currently working with about 200 hours of data to develop our analysis and calibration pipelines, so that when we do turn our attention to the 70 megahertz antenna, as well as the future data that's coming in, we hope that we can easily and quickly sort of sort through it and calibrate it, since we'll already have our methods set up. Okay, so let's talk a bit about the calibration of our data. So unfortunately, our ability to use a kind of direct calibration approach has been hindered by a lack of reliable S11 measurements. Basically, it's been difficult to get to the island, especially in the last few years, so we needed to adopt an approach that did not depend on having accurate measurements of the antenna's efficiency. What we have used instead is what we're calling the GSM calibration, which was first described in the SciHy paper by Tabitha Wojtek and collaborators in 2014. And here are some of the main equations from her paper. And basically the general idea is that you use the global sky model, or GSM, estimates of the sky temperature, to fit for a calibration parameter that will minimize the differences between the measured temperatures and those GSM estimates. So the calibration parameter here in this case is what we're calling K. So we have basically taken this approach and we have changed it a little bit for our own needs. So these are the equations that we're currently working with. The major differences is that we have taken the antenna efficiency and kind of put it inside of that calibration parameter K. And then also we are not going to be summing over time, so we are going to allow our calibration parameter to vary with both time and frequency. And essentially using this approach, after we solve for K to minimize this chi-squared equation, and then we remove the foregrounds from our data, which we've modeled with a third order polynomial, we are finding we get residuals around order unity, so between about 1 to 4 Kelvin. So this is a very simplistic approach, but it's been useful for right now to kind of get a general idea of the ballpark that our results are in. Okay, so looking forward on kind of the outlook for PRIZM, there are a few exciting pieces of news. So the first is that we currently have our inaugural winter over on site right now. So he is helping to keep the instrument in good health and keep the data rolling in. So it's very helpful to have someone present on Marion Island. And so we're actually going to continue to have full winter over support for the upcoming year as well. So hopefully with this winter over support, we're able to get some better S11 measurements as well as have the antenna up and running more consistently. And then another exciting piece of news is what I've already mentioned before, that we have a deployment coming up to Marion in the next few months. And so that group should hopefully be able to bring back the actual drives with the data on it from the 2020 and 2021 seasons. And so that's going to give us a lot more data to work with, which of course should improve our results. So thank you for your time. And again, if you have any questions, please don't be afraid to reach out on Slack to Kelly Foran.